All right, so now we're going to take a look at one very important aspect of chemical, or rates of chemical reactions, and that is the phenomenon known as catalysis. And this is something that is super important because catalysis involves the use of what's known as a catalyst. Catalysts are very important because they are substances. There are things that whose sole purpose is to actually increase the rate of a chemical reaction. Right? That's the whole point of the catalyst. That's what a catalyst does. That's the point of its existence. The other important characteristic of a catalyst is that it itself isn't actually used up. Okay, so a catalyst is there at the beginning of a reaction. It's something that we need to introduce into the reaction. It forces the reaction to go by a lot quicker, and then it's also at the end of the reaction. So what that means is that catalyst and then go back and can catalyze another reaction, the same type. So catalysts are very, very, very important. They're very powerful. Um, because the fact that they are regenerated at the end, that means that you don't need a lot of it to actually catalyze lots and lots and lots of reactions. So we saw a catalyst before in the previous section, looking at this particular reaction. We saw that in the slow step in this particular mechanism, we introduced the iodide ion over here. And then in the second step, step two, the iodide ion was actually generated. Obviously, when we add these together, they cancel out, so we don't see it in the overall reaction. However, it does appear in the reaction mechanism. So in this case, the iodide ion is a catalyst. Right? Remember, it is different than an intermediate. An intermediate is something that is generated in one step and then used up in a subsequent step. Here, the iodide isn't generated, it is actually added to the reaction. Okay? It does its thing and then it's regenerated at the end. So it can go into another reaction and catalyze that reaction also. So the way that catalysts work is that they are able to speed up reactions by providing a set of steps, elementary steps, with more favorable kinetics than those that exist without the catalyst, right? And typically that means that a catalyst will speed up a reaction by lowering the activation energy. Remember, the activation energy is A. And if you recall from the Arrhenius equation, right, we saw that the rate constant K is equal to A, the frequency factor A, times E to the negative activation energy over RT. So what that means is we can increase the rate of the reaction by increasing the frequency factor A, right? So we can, for some reason, somehow, if we are able to increase the number of collisions, we can increase the rate of the reaction. We could also increase the rate of the reaction by decreasing the activation energy, and that's where this part of it comes into play. And this is what catalysts actually do. They lower the activation energy. Okay, they lower that barrier or that hill that the reaction needs to overcome or to climb. And as a result, because that hill is lowered, more of the reactant particles are able to overcome that a lot easier, right? That's how typically your catalysts are going to work. So by definition then of what we just said a catalyst is, and what a catalyst does, we can say that the rate of a catalyzed reaction is always going to be greater than the rate of an uncatalyzed reaction, right? That is by definition what catalysts mean. That by definition is what they are actually able to do. So if we take a look at an energy profile of a catalyzed versus an uncatalyzed reaction, we're going to see a couple things, and it's important to note a couple of these characteristics. So if I take a look at, a second here, the energy profile of a normal reaction. So this one here on the left is normal reaction, meaning it's uncatalyzed. we see that the reactants, A and B in this case, have a particular energy associated with them, whatever this is over here. And then the products, C and D, have a certain energy associated with them as well, which is over here. And there is our activation energy that the reactants need to overcome in order to get from the reactant side to the product side. Now, in a catalyst, in a enzyme, in a catalyzed reaction, okay, over here, what we will see, what we will notice here is that the energy of the reactants is still the same as the energy of the reactants in an uncatalyzed reaction. Similarly, the energy of the products is still the same as the energy of the products for an uncatalyzed reaction. So those are the same. So the catalyst doesn't change, doesn't alter the energies of the reactants or products. Okay, what it does is it actually lowers this barrier or this hill. So instead of being super high, now it's a lot lower. So there's a lowering of the activation energy, right? So it's an alternative pathway through which you can get from the reactants to the products. Okay, so it's like saying, well, I want to drive from Oklahoma City to Dallas, right? I can take all the back ways, the back routes. It can take me a long time to get there, or I can take Interstate 35 and I can get there a lot quicker. Right? Instead of taking 5 hours, it takes me 3 hours to get from OKC to Dallas. But the starting point and the ending point is still the same. I haven't affected those. All that I've done is I've taken an alternate pathway. I take the interstate rather than taking all the back roads. So it's a similar idea here with your catalysts. So when we see we have a chemical reaction and it's being catalyzed, we sometimes refer to the rate constant as K, but you have the subscript C associated with it, and that's the catalytic rate constant, right? So we have the sub C there. This means catalytic or catalytic, to be more specific. So generally, we're going to encounter, we're going to come across three main types of catalysis. We have what is known as heterogeneous catalysis. We have homogeneous catalysis, and we also have enzyme catalysis. And we'll take a look at each three of these here in a little bit of detail. So the first one is heterogeneous catalysis, and it's the same term that we saw way back in Zen Chem 1 when we talked about heterogeneous mixtures, for example, versus homogeneous mixtures. In heterogeneous catalysis, the reactants and the catalysts are actually in different phases. So typically, the catalyst tends to be in heterogeneous catalysis, tends to be a solid, whereas the reactants tend to be usually gases or liquids. So what makes it heterogeneous is that the phase of the catalyst is different than that of the reactants. This tends to be the most important type of catalysis in an industrial setting. So on a commercial scale, making, for example, synthesizing different types of chemicals and stuff that we take for granted every day, heterogeneous catalyst tends to be the most common type that's used. And we also see it, for instance, a lot. We see it every day, use it every day, for instance, in the exhaust process of your internal combustion engine. So every time you drive a car or in an automobile, right, those emissions actually go through what's known as a catalytic converter. And in a lot of times, or a lot of instances, what we have happening here is the catalytic converter is itself made up of the solid there. Catalyst tends to be some sort of a metal. So you find usually precious metals, so things like nickel, or and that's Ni, or palladium, or platinum. So Ni, you have Pd, you have Pt. Sometimes you'll see chromium or copper. So either these are oxides of these things. These form the sort of like a scaffold that you see here And then your exhaust gases are able then to actually stick onto the catalyst that serves as like a substrate or a scaffold, I'm sorry. They bind to the thing, and then what happens is they get converted into these less, let's just say, harmful gases then that come out of the tailpipe, right? So normally in an internal combustion engine, okay, the types of gases that are produced, typically you have oxides of nitrogen. So for example, in a gas engine, you have, in addition to the fuel being burned, you have a bunch of nitrogen that's in the air. This gets converted, for instance, to nitrogen oxide. This, when it's released, okay, this can very quickly combine with oxygen to form nitrogen dioxide, NO2. And that is a major contributor to air pollution, things like smog and other things of that nature. We also see things like carbon monoxide being produced as well, right? And maybe other oxides that we don't necessarily want to breathe in. So that contributes to air pollution. So what happens is these things, right, they are the exhaust gases. They eventually get converted into less harmful things, such as nitrogen, N2, and O2 as well. This makes up the air to begin with, but this is way less harmful than the oxides of nitrogen or carbon monoxide, for instance, that can contribute to air pollution. So that's the whole point of having these catalysts, and these catalytic converters, right? They were able to speed up that process of converting the harmful exhaust gases to ones that are less harmful, not just to us, but to the environment as a whole. In contrast to heterogeneous catalysis, we have homogeneous catalysis. And here the reactions, both the reactants and the catalyst, they're in the same phase, right? And typically that phase tends to be a liquid. And usually what we're going to see, not always, but usually we're going to see acids and bases as the catalysts that are used in homogeneous catalysis and liquid solution. Right. So the example that's shown here is the conversion of this molecule. And you'll see stuff like this when you get to organic chemistry. This is something known as an ester. This is an ethyl acetate. This can be broken down by water into, we have acetic acid, and then we also have ethanol. So this normally proceeds by this reaction, and the rate law for this process is given here, and that's the uncatalyzed reaction. This can be catalyzed as an acid, and acids are generally, when you see them in a being used as a catalyst, you typically write them either on the reaction arrow, and if it's an acid, it usually is written just as an H plus, as a proton, because that's what acids do. And here it is, right? There's your thing on the arrow that tells you this particular reaction is being catalyzed by an acid. It's an acid catalyzed reaction is the way that we would refer to this. Okay. And the rate law for this is actually rate equals Kc. So there's the subscript that tells us it's a catalyzed reaction. And then we have the ethyl acetate, but then we also see that the rate here is actually dependent on the amount of catalyst, in this case, the acid that we have present as well. All right, so all of this is happening in the same phase, in a liquid phase or aqueous phase, for instance. So that's what makes it homogeneous. Now, the advantages, some of the benefits of homogeneous catalysis compared to heterogeneous catalysis is that the reactions typically can be carried out under normal atmospheric conditions. So we don't need, for example, high pressures for this to occur. These can be designed to function selectively, meaning that these catalysts, they catalyze a single reaction or a single type of reaction, as opposed to just all the reactions that we come across. And then most importantly, they tend to be generally cheaper because we don't need any of these super precious metals, things like palladium and platinum and chromium, etc., for the process to happen, right? So there are advantages to this. The third type of catalysis is probably the most important one for living things and human beings being examples of living things. And this is enzyme catalysis. And enzymes themselves, we define them as biological catalysts, right? So these are things that living things make. That's what makes them biological. And enzymes, again, their entire function is to speed up chemical reactions that are happening in your body, right? So enzymes catalyze. We'll refer to these as not just chemical reactions because they're also happening in a biological system. So we'll call them biochemical reactions. Okay, and I know a lot of you are taking organic chemistry after this class, and some of you may be going on to biochemistry down the road. You will talk a lot about enzyme. That makes up a huge portion of any biochemistry class that you take. And there's a specific type of kinetics that you will study when you get to that point called enzyme kinetics. And there are certain rules and equations and stuff that you're going to see down the road. That's a topic for a different discussion, a different day. Let's just talk a little bit about enzymes. So they're biological catalysts. Okay, living things make them. They catalyze biochemical reactions. And guess what? All of those reactions are happening inside of you right now. Okay, so pretty much all the reactions happening in your body, the human body, are catalyzed. They're sped up by an enzyme. Can you think about all of the reactions that are happening inside of you constantly? Every single one of them is being sped up by a particular enzyme. So they're very, 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 very important. It's hard to understate the importance of enzymes. Now, enzymes, not always, but typically the majority of enzymes are going to belong to a family of biomolecules called proteins. Okay, so most enzymes are proteins, not all of them, but most of them are proteins. And proteins are things that have a variety of functions. So for example, you have proteins that make up your muscles, for example. They make up connective tissue. They make up protective tissue. All of the antibodies that you make to fight off infections, those are proteins. Your hair, your skin, and your nails, those are made up of proteins. Your hemoglobin in your blood that transports oxygen, that is a protein. And most importantly, all the enzymes that catalyze the biochemical reactions inside of you, those tend to be proteins as well. All right, so enzymes, they can increase the rate of reactions. And not by a little bit, but they do it by a huge factor. So in some cases, by factors of millions of times per second. So 10 to the 6, or even hundreds of millions of times 10 to the 8 per second. And it's, or even more than that, 10 to the 18. So billions upon billions of times a second. And it's kind of hard to wrap your mind around that, but that's like, thousands of reactions happening per second. Okay, and that is extremely important. Now, the way that enzymes work, if you were to draw a simple picture of an enzyme, we have here our model. So there's our enzyme, and typically a protein, what this is right now. On the surface of the enzyme, you have this region, and that region is called the active site. And that active site is the region where the thing that the enzyme acts upon is able to bind. And the thing that the enzyme acts upon is called a substrate. Yeah, what you'll notice is that the active site actually resembles, if I were to outline the shape of the substrate, right? It's complementary to the shape of the substrate. So it kind of fits like this is kind of like a T, and the enzyme has a surface here, a shape that kind of looks like a lock, right? So only that key can fit into that lock, just like a regular lock of key. So this is actually known as a lock and key model. So it's not super complicated in terms of the naming. It actually makes sense. This is the lock and key model of enzyme activity. So the enzyme is able to bind to the substrate, or the substrate is able to bind to this enzyme, and forms what's known as an enzyme substrate complex, which we abbreviate as ES. So the enzyme here is an E, the substrate is an S, is how we abbreviate it. It forms this complex. The enzyme does its thing, which is to maybe help split this molecule into two, and then we release these, then are released from the active site. Those are your products. Product or P, the products they release. Okay, this active site over here is freed up, and this cycle can repeat over and over and over again. In some cases, thousands or millions of times per second. Right, and that's how powerful enzymes are. That's a general description of how enzymes actually work. Now, the treatment of enzyme kinetics, how we look at it mathematically, just like we did in the previous examples, is a little bit more complex and beyond the scope of our class. So for instance, you'll often see if you eventually take biochemistry down the road, you'll see the type of kinetics that you study that you're going to use is called the Michaelis-Menten kinetics. And there's a whole set of rules that you and concepts that you need to study, but this is what it's typically used to study enzymology and then enzyme kinetics as well. So the enzyme binding to the substrate actually forms an enzyme substrate complex. And that is typically a very fast step, right? So we have both the forward and the reverse reaction happening. We have the K1 for the forward reaction, the K-1 for the reverse reaction, just like we saw in the previous examples when we saw, mechanisms with a fast initial step, etc. So these are our elementary steps that we can use to help us determine or study, at least introduce at this case, on this stage, how enzymes actually work. All right, so again, E is the enzyme, S is the substrate, ES is the enzyme substrate complex, and then P is the product. So we often assume that the formation of the enzyme substrate complex and the decomposition back into the separate enzyme and substrate itself occurs rapidly, right? And we also assume that the rate determining step is actually the formation of the product over here. So what we can do is we can look again at the energy profile of an uncatalyzed reaction versus an enzyme catalyzed reaction. And what we'll see, again, we don't change the energy of the reactants and the products, they're the same. For a catalyzed reaction, enzyme catalyzed reaction, what we see is that there's a lowering of the activation energy here from the enzyme substrate to the enzyme substrate complex. So your EA is very low. And then from the enzyme substrate complex to releasing the product, okay, this activation energy is also low, especially when you compare it to the activation energy of an uncatalyzed reaction. So however you slice it, right, there's a lowering of the activation energy in the enzyme catalyzed process. So we can, in general, we can write the rate of such a reaction by saying the rate is equal to the change in the product, concentration of the product over the change in time. And then this being the rate determining step, we can say the rate is also equal to rate constant times the concentration of the enzyme substrate complex, right? The activation energy here is higher, so that's the slow step in this particular reaction mechanism. So if we were to, for example, plot on a set of axes, the rate of the formation of the product, right? So the rate of producing this thing here versus the concentration of the substrate, right? So the substrate is the thing that the enzyme is actually. And then this is assuming This is not written here, it's not written in your text, but this is assuming the concentration of the enzyme is constant. What we're going to see is as we increase the concentration of the substrate, right, we produce more and more and more products until we get to a point where now the rate of formation of the product tends to approach a constant value over here. And at this point, whatever that point is, what that means is all of the active sites of the enzyme are occupied. So that means all of the enzymes, enzyme molecules, these are all saturated, right? All of them, all of their active sites are occupied. So they cannot work any faster. And as a result, the rate of formation of the product is a constant. So as soon as a product is released, right, it's occupied by a substrate again, right? So we approach what's known as a constant value here. Again, this is assuming that we have the concentration of the enzyme isn't changing. We have a set amount of our enzyme.